Well, good morning, everyone. Welcome to Monday session. And today, the topic that we are going to discuss is instant center of velocity or instantaneous center of velocity. Let me share my screen, and then we'll get started with that topic. Okay, here we are. So today we'll go to over part one, which is an introduction. And on Wednesday, we will finish this topic. It's considered to be a relatively a fun topic compared with the previous topic that we have. It's more geometry. The material to study for this is the following session from your chapter 4. Again, chapter 4 on your custom book, which is equivalent of chapter 6, which has the title of Instant Center of Velocity. Please just study these sessions, session 11, 12, and 13. If you are interested and you have time to study the rest, that's okay. But these sessions are important to study. Examples, try to study this example 1 to 6. And also I have set up a problem set for you. We call it problem set 5, and they are all on Canvas. I will try to post the solution before your exam this Friday. So let's start this topic by a very simple example, which is a rolling disk. And when we say rolling disk, we mean a disk or a wheel that is rolling on a ground without a slipping. All right. So let's draw maybe one disk or wheel, whatever you like to call it. And let's say this is on the ground. Maybe use our ground as like this guy. So this is a fixed ground. Okay, this is the disk. And let's assume that this disk is rolling with omega, angular velocity of omega. Okay, so what we can say about this disk, I want you to focus on this point, the point of contact, let's call it point C, C standing for contact. And obviously we know that if I draw a perpendicular line from this point C, it's going to pass through center, right? So that's something that we know for sure. And let's call the center O. So what do we know about point C? Well, can we say for a very moment, let's say for an instant, a very short period of time, we can assume that point O is rotating about point C. Can we say that? I want you to visualize a very, very large wheel, and this wheel is on the ground, and you look at this point O. Can we say this point O for a very tiny time is spinning about point C? In other words, I'm just going to exaggerate here. Like this blue line is rolling. Can we say that? If we can say that, then it means we are assuming this disk for a very short period of time is being pinned to the ground. Okay, so I just say it one more time because it's important. This disk is rolling. There is no slippage, right? This point C is not a slipping. If we have a camera looking at this disk, so this point C is not a slipping, is not moving along a straight horizontal line. That's considered to be a slippage. But without a slipping, we can assume this disk is rolling. And for a very, very short period of time, we can assume that this point C is the center of rotation for point O. Like in other words, point O is rotating about point C. So in that scenario, I can assume that for a very short period of time, this disk is being pinned to the ground, okay? It's more like, let me move the whole things to other side. So if I duplicate this guy, bring it back here. So I can assume that this is like more like a pin. So I write it down for a very short period of time. So this is what we call it an instant, right? Which is like, you can assume it's a time almost close to zero, like 0.000001 seconds, something like that. So in that case, can I say that velocity of point C is zero? Can I say that? Most likely I can, right? Because if it's not moving and point O is spinning about this point C, so we imagine that this point C is a pin for an instant, then we can assume velocity of point C is zero. Again, don't forget, just for an instant, okay? For an instant. So this point C that has velocity of zero for an instant, we call it instant center of rotation or instant center of velocity. So we call point C an instant center of rotation or velocity. People use different names. And just out of laziness, we use sometimes the short abbreviation of IC, instant center. And sometimes if we call ground 1 and we call this disk 2, people show this point C as an I1, 2. Okay, different forms that then people show. I1 and 2, it means an instant center between point 1, between member 1 and member 2, which here member 1 is ground, member 2 is the disk. Okay, so that's one thing. So let's stick then with this notation in this course. 1I2, then we mean instant center of velocity between point 1 and 2 at this very moment, and this is the point that these two are in contact. So what is the velocity of point O then? Point O, if the disk is rotating about point C, and if we have a camera, we can notice that point O is moving along a horizontal line. What is its velocity? Should be very easy. So it's gonna be R omega. What is R? We know R is the radius of this guy, right? So R is the radius of this disk. So that's the velocity of point O. So VO. Now that we are in the topic of instant center of velocity, let's also assume that this guy, this disk, has also an angular acceleration, alpha. Okay, so it has an angular velocity and it has an angular acceleration. So from what we learned before, we should immediately be able to say what is the acceleration of point O. So point O should have an acceleration in this direction, and it should be equal to, let's call it AO should be equal to R alpha. Now you tell me, do we have a normal acceleration for point O? I want you to tell me or type in a chat if point O has a normal acceleration. Remember, always in this course, we said a point that is moving has two accelerations. One is normal, one is tangent. Here we know the one of them, it is AO is R alpha. Do we have a normal acceleration? Yes or no? I'm gonna check chat and see what you guys are saying. No, we don't. And so, but Kihomi is suggesting we should have a normal acceleration. Okay, then let me give you a hint. What is the path that point O is moving? Point O is moving on a straight line, right? It's true we have an omega, but what was the formula for normal acceleration? It was V over 2 divided by R, right? So the normal acceleration, I'm just going to write it down here. AN is V divided by R. The radius of the path, right? Not the radius of the disk. Here, because we are moving on a straight line, R is infinity. So it is then equal to 0. So it is V2 divided by infinity is equal to 0. Okay, because point O is moving on a straight line. So that's about it. Then when you have a disk and this disk is moving on a straight line, like on a flat ground, because if it was not a flat ground, that would have been a different story. Then its center has a velocity R omega, an acceleration R alpha. It doesn't have a normal acceleration. But we're going to have a more important question. What about AC? What is the acceleration of point C? We saw that it doesn't have any velocity, VC is 0. What is its acceleration? And it's a $64 question. Many students and many engineers give a wrong answer. I give you just a hint. 0 as well. Okay, what about others? Do you think point C has its acceleration is 0? Okay. I want you to visualize this point C, its movement. Point C, by the way, belongs to this disk. It's part of this disk. Okay, it's a point on this disk which at this very moment, it is in contact with ground. Okay, it's a contact point between disk and the ground, but point C is moving on this disk. So if it's moving on this disk, what is its motion? Is it a straight line or no? It's more like a curve motion. It should be a curve motion. Try to imagine that you put, let's say, a point on this disk. Let's put this point guy here, like the one that I just highlighted by yellow. So this disk is rolling, and this point for a very moment, at one time, it is come and touch the ground. At that very moment, its velocity is 0, but this point is keep rolling, right? Its velocity at that very moment is 0 because everything is rolling about that point. But it's moving, right, on a curve. and it should have an acceleration. Let's calculate that acceleration. So we learned before, if we know the information for point O, we are interested in knowing about the information for point C, we can then write down that acceleration of point C is equal to acceleration of point O plus AC with respect to point O. And keeping in mind that these guys, they are all vectors, right? So this is then a vector, this is a vector, and this is a vector. So like always, let's set up an X and Y coordinate, and we are free to choose wherever we want for our coordinate. But let's set the center to be the origin. So then let's have like this direction to be X and this direction to be Y. And our center is point O. So what is the acceleration of point O? We just calculated. It is R alpha, and its direction is in X direction, which we learned, we show it by I for simplicity. What is the acceleration of point C with respect to O? We discussed this before. We said when we say a point with respect to another point, it means that point, like here, point O, we consider it to be fixed. Let me move my disk here. And this is point O. And this is point C. So we talked about it before that when we say point C with respect to point O, it means that we assume point O, like we visualize that point O has been pinned to the ground, or in other words, we are sitting at point O and we are looking at point C. So all we see is this point C is moving around us, right? So this is the meaning of point A with respect to C. Point C with respect to O. So C with respect to O. So observing C with respect to O, okay? So then in that case, what is the acceleration of point C? It is rotating with omega. And also it's rotating with alpha. Can you guys tell me what is its acceleration? Like point C. Forget about this disk and everything. Just look at this image. We have a disk, it's pinned to the ground at point O, and the person sitting at point O, look at point C. So, and the disk is moving with alpha and omega. So you should be able to tell me immediately, which, yeah, you're right. Some of you wrote. This point should have a normal acceleration because it's moving on a circle, and a tangent acceleration. Look at the direction of alpha and omega. So this is R alpha and this is R omega squared. So let's then put them in I and J here. I will have R omega squared J minus R alpha I. Okay. So this is all acceleration for AC with respect to, and this is AO. So let's do the math here. What we will get, we are going to get R omega squared J. So what did we found? We found that point C has an acceleration. I mean, this acceleration is upward, and its value, so I'm going to write it down here, is R omega squared, and it's upward. Okay, its direction is going up. So it's an important then conclusion here. if we have an instant center of velocity, if a point, its velocity is zero, like this point C, we see zero, it doesn't mean that its acceleration is zero. Like in this simple example of the disk, it has an acceleration, it is r omega squared. And we prove it where it comes from. Now I have a question for you guys. What if r omega squared is bigger than gravity? What will happen? Can you tell me? A disk is moving and omega is so large, right, that if we multiply r omega squared, it will become bigger than gravity. What will happen? Can you tell me? So gravity is coming down. This is gravity, right? Now our disk, this point C, has an acceleration that is bigger than point G. What will happen? Any idea? So most likely, if we have an acceleration, right, at point C, which is bigger than gravity, the disk is gonna separate from the ground, right? And that's a topic that in next chapter, we're gonna discuss it more, but simply, you know, when you have an acceleration, the Newton law, remember from previous lecture is m multiplied by a. So because of gravity, you have an mg. Because of this r omega squared, you have an mr omega squared. Now the force coming from this guy is become bigger than weight. So mr omega squared f multiplied by m multiplied by a is become bigger than weight. And then a separation, right? Separation of the disk from the ground, which is not the focus of the topic for today, but just something to keep in mind. Okay, with that introduction, then let's get into a more general case. Rather than just having a disk, let's assume that we have a body, a rigid body, and this rigid body has a general motion. Remember, a general motion, the body can rotate and also move, okay? So, and then let's say as a general assumption, we draw a point A on this rigid body and point B, and point A is moving on a curve, point B is moving on a curve. And at this very, very moment, we can assume that the curve that point A is moving is part of a circle. And point B is moving on a curve, which at this very moment, we show a part of that curve, which we can assume for a very short period of time, that portion of curve is part of a big circle, right? So if I have this scenario, and let's say point A has a velocity, point B has a velocity, I want you to focus only on point A. If point A is moving on a circle for this very short period of time, let's find that the center of that circle, well, it should be somewhere on this line, right? That's the center of this curve at this very moment should be on this line. And we all know that this angle has to be 90 degrees because velocity is normal to the path, and this line is the normal line, which is the center of this portion of circle. We'll do the same for point B. We know point B also has to be, let's say, perpendicular to this guy. Like this angle is 90 degrees, right? And the center of this curve, this circle that point B is moving, has to be on this line. So what we have then, the center of for this curve A has to be on this line. The center for this one has to be on this line. Then can I make this conclusion that the point that these two line intersect is the center of rotation for this part at this very moment, okay? Again, it is important, and I want you to pay careful attention. We have a rigid body, it's moving on a general motion, so it's not rotating about any point. But at the for a very short period of time, if we look at just one point of it, point A has to move around a circle because it is on a curve, and that curve is part of a circle which has a center. The same for point B. So if point A, point B, they are both rotating about one center, and both of these points are part of a rigid body, it means the center of these two has to be the same, which we showed it has to be the intersection of these two lines. So with that, then logic, we can say that this is the instant center of rotation, IC, instant center of rotation for point A and B. Why it is instant? Because let's look at another moment, let's say 0.1 second later. 0.1 second later, maybe point B is here. Okay, so this is point B, and maybe point A is, it's here. Okay. So then this is B prime, and this is A prime. Okay, so the same assumption as we just said, point A prime is part of a circle, then it has to rotate on a circle, and its center has to be on this pink line. What about point B? Point B has to be on this line. Therefore, this is the new IC. Okay, so as you can see, this point IC instant center is keep moving, but at a very short period of time, at the very instant, we can assume that the whole body is moving about that point. And this point doesn't have to be on the rigid body. You can see it is off the rigid body for this example, but might be in some example that it is on the rigid body. It's an imaginary point that we can imagine for a very short period of time that the whole body is being pinned to the ground at this point IC, but this point IC is keep moving, as you saw it in this example. Okay, hope it's clear, because that's the foundation for the rest of lecture. If it is clear for you guys, now let's have this general motion in one example. Let's say I have maybe a 4-link. Maybe let's do it over here. Yeah, let's say we have a 4-link. This is a joint here. This is a joint over there. And we have a joint to the ground. And a joint to the ground. And what else do I need? Okay, so this is then has been pinned to the ground. And this guy also has been pinned to the ground. Okay, so let's, like always, we call them by numbers. This is 1, which is ground. This is 2, this is 3, and this is 4. So what we see here, link 2 has just a pure rotation. We know that, right? Point 2 is moving on a circle. It's a pure rotation. What about point 4? Point 4, pure rotation, is moving on a circle, like on a big circle about this point B, maybe. Let's call it A and this one B. All right. So what about 3? Link 3, can I say it has a general motion? Like when this mechanism is moving, let's say if I have an omega is moving, right? Can I say that this link C is rotating and at the same time is moving? It has a general motion? I'm sure we can, right? So if it has a general motion, I want you guys to have a piece of paper, and I'll give you 1 minute. Try to find the center of rotation for this link 3. Okay, so this is the example we're trying to find. So this is the example. Link 3 has a general motion. Find its instant center at this moment. Okay, that's the goal. And you have 1 minute. I'll let you guys try to think about it and then tell me what is the center of rotation for this guy. Then I will call somebody to come to the table, not table, on a screen here and draw that center for me or for the rest of us. So I'll give you a hint. So think about, let's call this one O1 and O2. So this one to be O2 and O4. Let's keep this one A and B. Okay. Think about this link 3 as the same picture that we have on the left. So we have part AB. And we want to find out the center of instant center of velocity for this link 3. So if you could find this the center of velocity for this link 3, I want you guys to try something. With your Zoom, you should find something which is called annotation. Can you guys locate it and find it? Annotation should be somewhere maybe on your screen, somewhere where there is 3 dots. And if you click on annotation, then you have a bunch of options. One is drawing. If you click on drawing, then you should be able to find something for a straight line. And I want you guys try to draw whatever you had in your paper here on the screen for me. Anybody? So anybody could find that annotation? Okay, great. So thanks, Akhilesh. Yep. All right, so almost done. We did a good job with, I guess, mouse. You're trying to draw this. Great. So that's, in fact, the answer. So what about the rest of you guys? Do you agree? You can type it in the chat if you think Achilles was right, what he draw on the screen. Alex, yep, that's true. So yes, what if you guys got the same answer? It is true. Let me now try. So Achilles, I guess you should be able to close your annotation. Okay, thank you. So they were right. So point A is moving on a circle, and this is its velocity, right? This is velocity of point A, and this is velocity of point B, tangent to this circle. Tangent to this circle, we know that it means being perpendicular to this line. And then the next is, we know that we have to draw a perpendicular line to this velocity. So that's one line, and this is another line, right? But we also know something else. We know that this line, this pink line that I draw, they are extension of link 2 and 4, because link 2 and 4, they are also perpendicular to this velocity, right? So then we can here make a nice conclusion. If I extend this link 2 and this link 4, I will get, 1, 3. The instant center of link 3, okay? So now that we are here, can I say this point is the instant center of 1 and 2? In fact, it's not an instant center, it's a permanent center, right? Because this point is not moving, it's not going anywhere, but we call it I12, an instant center, which is a permanent center. And what is about 0.04? This is the instant center of between 1 and 4. Remember, instant center is a point where a part is rotating about it. So what about these 2 and 3? This is the instant center between 0.2 and 3. Because look at 0.2 and 3. 0.2 and 3, they are pinned at this point. They are joint, right? And what was the definition of instant center? A point where two members, they are spinning about that. And this is I3, 4. Okay, so one more time, and I want you to have all your attention here. We struggle to find the instant center for link 3. This is I13. And this instant center, it's a point that you can visualize that for a very, very short period of time, this link 3 has been extended. It's more like a plate. Okay, this link 3 is part of this large plate that for a very short period of time has been pinned to the ground. But this pin is temporary. In a next moment, the position of this point is going to change. That's why we call it instant center. But link 2 is always, its center is going to stay the same. I12 is always the same. And I14, it means the center of rotation between link 4 and ground. 2, 3, it means the center of rotation between link 2 and link 3. Okay, so this is the meaning of 2, 3, the instant center between link 3 and 4. And the same for I3, 4. So if you guys agree with that, I want you to tell me what you notice about these 3 points. I12, I23, and I13. What do you notice about these 3 points? And you can type it in a chat. Here is the question. So 3 points. I2, I12, I23, and I13. Anything on the chat? Collinear, that's true. So you guys are right. So these 3 points are on the same line. So they are on the same line. What about these 3 points? I14, I34, and I13. They are on the same line, right? So let me write them down here. Move it a little bit out of the way. So 3 points, I14, I34, and I13 are on the same line. Okay, so these 3 on the same line on the left, on the right, these 3 on the same line, they intersect, and as a result, we could find I13 for this mechanism. So if you notice that now, you should be able to realize one good formula in geometry, that if I know one I12 and I23, like these 2 points, and if I know I14 and I34, the 2 points on the right, which we know them because we know that they are like the joint, right? If we extend those lines, or if we draw a line, the intersection of them give me the center for the other part. With this, and hopefully if you could follow this and the logic behind it, these 2 guys, Kennedy and Arnold, and they have nothing to do with the Kennedy, the president, and Arnold, I guess, the governor of California, the 2 scientists, long time ago. Maybe they were friends with Kennedy and Arnold, I don't know. But they developed these 2 theory, and we're going to use that. So their first theory was that a mechanism with n member has n multiplied by n minus 1 divided by 2 ICs. Let's see if they were right for the 4-link mechanism. 4-link mechanism. So n is 4, like it's a 4-link mechanism. So number of then ICs is equal to 4 multiplied by 4 minus 1 divided by 2, give me 6, right? Is that right? Yep. So let's move back. Now let's see how many we found here. 1, 2, 3, 4, 5. We need another one, which we are going to find. We find 3, 4, 2, 3, 1, 2, 1, 4. Okay, so that's the first theorem. We'll get to the second one. The second one is more important. This is what we saw, is for any 3 members, M and P, the 3 center of instant center, they are collinear, as we saw in this example. Like the 3 members here, 1, 2, and 3, like for this scenario, members 1, 2, 3. The 3 of them, they were on the same line. And the same for 1, 3, and 4. Okay, So that's then their second law or theorem. And we can use these to find the center of velocity for a mechanism. And I want you guys try this for me, and you have 1 minute to find the center of instant center of velocity for this crankshaft mechanism. To be consistent, let's call one to be ground. This is member 2, this is member 3, and this is member 4. So number of ICs then is 4 minus 1 divided by 2, 6. You should be able to find 6 instant center, and please try that and find them. You have 1 minute. So again, as a hint, first start with the obvious one. The obvious one are the one that you know that they are joined. Like this guy is 1, 2. This guy is I between 2 and 3. This guy is I between 3 and 4. And you should be able to find 1 I4. If you could find 1 I4, then the problem will be solved. But I will give you 1 minute to think about it. And then we will be done for today. First, try to figure out the instant center of I14. I will give you another hint. So this part 4, we are almost done, guys, in a couple of minutes. This part 4 is moving on a straight line, right? If it's moving on a straight line, what is its center of rotation? So if this slider is moving on a straight line, what is the center of rotation? Any idea? Can I say that the center of rotation for this point 4 is at infinity on this line, so perpendicular to the path, and this is I14 at infinity. It might be at infinity in the sky, or it might be I14 at infinity at the center of, let's say, Earth, right? Because this is a part moving on the center of Earth. So then I14 can be at infinity. Or somebody may say, no, it is in the sky somewhere. But they are at infinity, it doesn't matter. At infinity, but on this green line. So here we have, so we have I12, I23, and I14, and I want you guys to tell me where is the I13. And let's stop here. You can think about it, and on Wednesday, I want you to find this 6 center of instance center for me, using all the information that we have. Which information? We know that every 3 center of velocity, they have to be on the same line. And here we have 1I2, 2, 3, 4, and 1, 4. We have 4 of them. We want to find the rest. Okay? So we want to find 2 more. And that's 1I3 and I24. Let me write it down here. And the same for the previous example. I want you to find the 6th one, which is I24. All right, so solve this example and this example, and maybe also, if you have time, try this example too. Good luck with your midterm, guys, and see you all on Wednesday with the rest of this lecture.
Professor, I had a quick question. I was wondering
Okay. Have a good day.
when you're gonna